Okay, let's move on now from phase transitions and talk a little bit about solutions. So I guess let's start by talking about what happens when you form a solution in the microscopic sense. That's kind of how I like to think about things. So if you have, let's say you have a lattice of sodium chloride. Okay, so I've got something like this, and these are my chlorides, and this is my sodium. And those are sort of alternating. Here, let me just use some colors. It's easier. Yeah, so I've got sodium and chloride, and they're alternating in the structure. So this is table salt. So, when you go to get french fries and you put salt on top of them, this is what it looks like. This is sodium chloride. And so the orange ones are sodium plus, and the Cl is Cl minus. If you don't have your anions and cations and stuff down, like you can't write out sodium chloride and don't see this sodium plus and Cl minus. I would start studying that now. I don't know how hard we're going to hit it in this first unit, but like it starts to become really hard later on in the semester. So you should be able to say like, oh, I know magnesium chloride looks like this, or like sodium sulfate looks like that. That's something that we expect you to remember from part one, and you don't want to be memorizing all your polyatomic anions and stuff right before the exam. So start studying that stuff now. But anyway, so I've got sodium chloride salt that looks like this. So just little salt crystals, if you're looking at it macroscopically, look kind of clear and white. What happens if I dissolve salt in a glass of water? Reasonably sophisticated process, it turns out. And we'll get a kind of a good overview of what that is. So I've got water here, and I'm putting in my salt crystal in there, and I stir it up or whatever, and the salt breaks up and dissolves. So what does that look like macroscopically? Not super interesting. What does that look like macroscopically? So if I dissolve this, as I wait long enough, what do I end up seeing? It just looks like a glass of water. I can't even tell the sodium chloride's dissolved in there. So what's going on there microscopically is actually reasonably complex. So as the salt dissolves in water, I have water molecules. So right now we're looking at chemistry. We're looking at a lot of the intermolecular forces. We're not talking that much about covalent bonds breaking and forming. We're looking at ionic bonds and hydrogen bonds and stuff like that. So if I look at this, it has dipole moments. So these little Greek deltas here just means small. So delta positive. So remember, this means big change. This is the lowercase delta, and it just means small change. And we use them to represent dipoles because obviously the dipole on a molecule where you're dealing with atoms is extremely small. But so it has dipole moments. The hydrogens are positively charged, and the oxygen is negatively charged because the oxygen is electronegative, so it's pulling some of the electron density towards itself, increasing its negativity, and the hydrogens are losing electron density, which reveals a little bit more of their proton, which makes them positive. And so my salt crystal up here, when it dissolves in water, man, I really got to get better at this iPad action. Maybe I can take this one. All right. When it dissolves water, I'm sorry, when the come with me. Oh my god. All right. I'll was trying to be real smooth. It did not work. So remember, these are sodiums. Let me draw this a little bit bigger. And this is chloride. And so these don't have dipoles on them. They are actually have formal negative and formal positive charges. Let's label the positive part in red. So these positive parts here can interact with the negative on the chloride and sort of stabilize that negative charge. The other side of the water molecule, which is negative, which we can label with, I don't know, about hot pink, that can stabilize the positive charge on sodium. And so what ends up happening is you form bonds through these dipoles. Now label those with pink. So the negative parts of that dipole interacts with the positive charge on the sodium, so you form a bond. And then over on the other side, over here, the same thing happens. The positive parts of the hydrogen form bonds with the chloride anion, which is negatively charged. So really we're just saying opposites attract, and in this case, we're looking at the opposite charges on the edges of molecules, but it's not any more sophisticated than that, although the pictures look pretty wild in abstract. Okay, so clusters of water molecules form around these anions, and depending on anions and cations, depending on which one it is, they either face their positive hydrogen atoms towards it or their negative oxygen atoms towards it. So this is what's happening. So if we had to describe this, to go back to what we learned in our first lesson, is we're forming bonds. We're forming bonds. And the bonds we're forming are between the solute and the solvent. All right? What do we know about forming bonds? This is one of those things where I was like, you should memorize this because it's really, we're going to talk about this a lot. When we form bonds, we always have an exothermic process. So this is exothermic, which means that delta H for this process is negative. And we can call that delta H, we'll give it a little subscript of solvation, but we're always talking about enthalpy. The subscripts are just really for bookkeeping. So delta H of solvation, because we have formed bonds, it's going to be negative, so it's going to release some heat. This is a good thing for the system. It's favorable, you might say. But what's the other thing that's happening here? What's the other thing that's happening here? We're forming bonds. That's, ooh, God, I'm really having some IT issues here. The other thing that's happening here is with the sodium and the chloride. So I'm going to tempt fate and try and move this picture again. Oh, it's working. No. Okay. So yeah, so when we've got this sodium chloride crystal, it's true that we're forming bonds, right? But in order for those bonds to form, what has to happen here? These things have to actually break. Close enough. Okay, so that crystal flies apart. Okay. Anyway, so you get the idea though. These bonds in the what we call the lattice of the crystal. Those break up. Okay, so here we're breaking bonds. Breaking bonds, and we would say, like, I don't know, maybe between ions in the crystal. And so we know that breaking bonds is always endothermic. And that means that the delta H for that will be positive, and we're going to call that the delta H lattice energy. Okay, so the delta H associated with breaking up the crystal is called delta H lattice energy, and it's positive because breaking bonds is always positive. The delta H associated with forming bonds between the solute, which is the sodium and chloride that we just broke up, that's going to be exothermic, and we're going to call that delta H of solvation. We can take the sum of these and say that delta H of solution is equal to delta H lattice energy plus delta H of solvation. Okay, so what is delta H of solution? Generally speaking, well, so obviously it depends on the lattice energy and also on the solvation energy, the delta H of solvation. Generally speaking, the delta H of lattice energy is going to be ever so slightly larger than the delta H of solution. That means the delta H of solution is generally going to be positive, although it's not always true. And this is kind of how chemistry works. We have a lot of like, this is kind of true most of the time types things. So it just depends on the crystal, and it depends on, it mostly just depends on the crystal. I guess it also depends on the solvent as well, as far as whether the lattice energy and the delta H of solvation are going to be about equal. So generally speaking, the delta H of solution is maybe, I'm just going to say like, I'm going to put slightly here. We're going to say that delta H of solution is usually close to 0. And you should have some intuition of that. So, like, when you take sodium chloride or sugar or something and dissolve it in water, you don't feel like you don't feel a big temperature change. So if the delta H of solution was strongly exothermic or strongly endothermic, that would mean that when you put sugar into like a glass of water, you would expect to either see like tons of heat come off, or you would expect it to get really cold. And really, we don't see either of those things happening. The temperature change is really subtle, and so it sort of tells you from your own intuition that delta H of solution is generally pretty close to 0. And the same is true of sodium chloride. It doesn't really change the temperature of water that much. It's not always true. Examples of things where it's not true are like, have you ever had one of those ice packs where you break up, it comes in like a clear bag or like a plastic bag, and you break it up and it gets cold? That's something where the delta H of solution is actually very endothermic, and so it cools naturally. And vice versa, the ones where you could break it up and it heats your hands and your pockets, that's a thing where the delta H solution is very exothermic, so very negative. And so there are obviously exceptions to this rule, but in everyday life, and for most of the stuff we're dealing with here, we can just assume delta H of solution is either close to 0, unless you're given the delta H lattice energy and delta H of solvation, like the actual numbers for it, in which case you can just calculate it out and you'll know. So that is how enthalpy of solution works. And you can see that even though the analysis gets kind of wonky here, right, I'm drawing all these kind of complicated pictures, most of my analysis, when it starts getting into the classical thermodynamics, which is one of the more important parts of sort of understanding this, comes down to forming bonds, delta H is negative, breaking bonds, delta H is positive, right? Breaking bonds is endothermic, forming bonds is exothermic. That's sort of what we're building. Those are our like primary axioms or whatever that we're building most of our understanding of this chemistry off of. So even though they're little snippets, it's a powerful kind of little snippet to know.